All right, hello everybody. Okay, so here we go. We are going to review 12.1, and we're looking at page 632. All right, now, the triangle proportionality theorem, which is what's on that page, let me just put our own little spin on it. So if we start with a triangle, you don't have to write this, just follow along. You can look in the book, because we're going to do pretty much the same thing. But you've got to connect what I'm saying to what you're seeing. Okay? So you're going to be looking back and forth between what I'm writing and what's in the book. Here we go. Now, there are three sides to this triangle. It does not matter which side that I draw a parallel line with. Okay? It does not matter. All right? Sears, you get to choose. I'm going to go like this, this, this. All you got to do is say stop. Okay, she chose this one right down here. So I'm going to draw a line. Does not matter where, but this line that's going to be drawn is parallel to this line. This side. Everyone okay with that? And we'll go about here. Chris, how's that? Does that look parallel? Not bad, huh? All right, we'll take it. Not great, but not bad. We'll take it. Okay, so those are parallel. So that's what those little arrows mean. They're parallel. Now, excuse me. The triangle proportionality theorem says this. If these are parallel, there are four segments created. Look at this. We're going to call that one A, from here to here. We're going to call this one B, from here to here. Make sure you're following along. And we're going to call this one C, from here to here. We're going to call this one D, from there to there. Everyone with me? See the four segments? Now, we're going to write them in a proportion. A is to B as C is to D. That is always true. We're not going to prove it. They spend time proving it. We're not going to. We're just accepting it. That theorem is true. Does that make sense? Pause. What that would look like if I put numbers in would be something like this. 5 is to 1 as, I don't know, let's see, 10 is to 2. So if I were to get my ruler out and actually measure and say A is 5, C is 10, B is 1, and D is 2. Now how can I verify? Well, if I want to verify, that's a word that they use a lot, I'm just going to use the proportion and solve. What's 5 times 2? 10. What's 10 times 1? 10. Verify. That makes sense? How we verify. Everyone okay with that? Yay? 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 Okay, good. Well, let's investigate this just a little bit more. All right? Because that's not the only way to solve. Because I could just look at it as simple ratio. What's 5 divided by 1? Go ahead on your calculator. What's 5 divided by 1? What's 5 divided by 1? Thank you. What's 10 divided by 2? Huh. See, a proportion is actually just equal ratios, which means equal fractions. That's another way of verifying. So am I cross-multiplying when I do that? No. Does that make sense? We're following along? All right, let's do another one on the same figure. So it's going to get a little bit messy, so stay with me. All right, so let's say that we've got a parallel line right there. Parallel, parallel. Now we've got 4 segments. We've got one here, there, here, and there. Now let me highlight those. I'm going to color them in. There's 1. There's 2. There's 3. Here's 4. Everyone see those 4 segments? Okay, let's put it a little bit. What about this line and go across? Okay? In other words, if I go A, B, C, D, can we say that A is to B as C is to D. Is that acceptable, Ploff? What do you think? So I didn't go from segment on the same side. I went across. A is to B as C is to D. Do you think that's acceptable? Off. You had an answer. Now you're doubting? Yes? Yeah. You are. Correct. Yes, that is acceptable. You see, when you have a proportion, so compare, look at this proportion as compared to the original proportion. They're basically the same, right? But the segments are different in where they're at. B on this one represents what we had as if we were going across, which would have been C. Okay? So it's okay on a proportion to kind of go across. And then here to here. All right? Does that make sense? Okay. Look at the next page, which would be 634. And it says the converse of the theorem basically just means that if they are in proportion, then they are parallel. When I say then they are parallel, what's that mean? The segments. That means the side of the triangle and then the line segment that we put in. Okay? So if I can show that they're proportional, equal ratios, then I know that they're parallel. Okay, so it works both ways. All right? Everyone good? All right, let's turn. The assignment was page 630. This started in 637, I think, 3 through 12, I believe. It was due last night. 637, 3 through 12, I believe that was the homework. Does everyone remember that on Canvas? You know what? Okay, so let's take a look at number 7. All right, so I'm going to draw it up here. We go number 7. We got, this is your homework. We got a line here. We got here. Let's focus in a little bit. A little bit more. Okay, so now we got PMO. PMO, and then we've got PNR. Okay. Everyone okay with the picture on number 7? Now we move along. We know that, we got a decimal. Well, you might need your calculators. Might as well get them out. 2.7, and we got this one is at 3. And then we know that this entire length here is 10. And we know that this entire length is another decimal. No, not a decimal. It's 9. There. Okay, so let's do some quick math. What's 9 minus 2.7? That makes this 6.3. Thank you, guys. 10 minus 3, I can do that one. 7. All right, now let's set up a proportion. You know, because the directions say verify that MN is parallel to OR. Verify. Okay, so what's that mean? We need to show they are in proportion. That's what the verify means. We show that they're in proportion. So we're going to set up a proportion. Here we go. 6.3 is to 2.7 as 7 is to 3. Okay, cross multiply. What's 6.3 times 3? 18.9. Thank you, Chris. What's 7 times 2.7? Look at that. Verified. We'd be done. Is that the only way to do it? No. Let's take a look at a couple others that would also work. Okay, watch this. What about 6.3 to 10 and 7 to 9? Look at that. That's kind of crazy. That's 6.3 to the opposite side, and then 7 to the... All right, well, let's check. What's 6.3 times 9? Okay, thank you, Chaz. And what's 7 times 10? Oh, no, that's weird. Yeah, 7 times 10. What's that? Does that work? No. What happened? Because we didn't compare the opposite sides. We were on the same side. See how we went 7 to 10? On the same? See that? Okay. So what you have to do is you have to make sure you're using the proper side. So this one doesn't work. What if we did this? What if we went 6.3 is to 9? As 7 is to 10. Would that work? Yeah, let's check. 6.3 times 10, that's 63. 9 times 7. See the difference? How you have to set up the proportion. One last thing to set up the proportion. Okay? We can show that they're equal ratios. Okay, what's that mean? Well, if I take 6.3, go ahead on your calculator and take 6.3 and divide it by 2.7. What do you get? Should get 3.3 repeating, yeah. 3.3 repeating, or that's the same thing as 3 1/3. Everyone with me? What's 7 divided by 3? 3.3 repeating, or 3 1/3. See, what happened is, again, we're not cross-multiplying. We're just showing that they're equal ratios. And that works. That works. You see that? Sears, you see that? So, it's not using the triangle proportionality theorem and using a proportion, but it's still showing or verifying that those lines are parallel. So I could come back and say, yes, those lines are parallel. That makes sense? Nuzzly? That makes sense? Piece of cake, right? All right, good. Okay, so let's, if you don't have that assignment submitted, and some of you don't, make sure you get it submitted. Let's take a look at another problem. Now, this is from 12.2, okay? Now, 12.2, I'm just going to give you there was an intro video yesterday, okay? So if you watched it, great, okay? I'm just going to give you kind of the basics of 12.2. Let's say that we have a segment right there. There's a segment. And we want to divide that into 5 equal segments without using a ruler, without measuring and then dividing by 5, right? Without using a ruler, we want to divide that into 5 equal segments. How in the world can we do that? Well, it's actually not very difficult. Watch. You don't have to write this down, just watch. I'm going to create a ray down there that intersects with one of the endpoints. Does not matter which one. Okay? And then, my gosh, we haven't touched one of these in a long time. I'm going to use my compass, and I'm going to have a random width. Does not matter the width of my compass. Does not matter. Okay? And I'm going to start at this vertex right here. And I'm going to make 5 equal arcs. Okay, 1, 2, 3, 4. Everyone okay with those 5 equal arcs? Okay, then I'm going to use a straight edge. Straight edge. And I'm going to connect the last one, the 5th one, to the other endpoint. What am I creating? I am creating a triangle. Everyone okay now? All right, so now what do I have? I have a triangle, and one of the sides is already divided into 5 equal segments. So, do you see this angle here? One of the vertexes of the triangle. I'm going to copy that angle. So I'm not going to go through the construction part of copying an angle, just letting you know, theoretically, that's what I'm doing. Okay? I'm copying this angle right here. And so when I do that, I end up with a parallel line. I do the same thing here. I have another parallel line. Same thing here. Another parallel line. Look what happened. I now have 1, 2, 3, 4, 5 equal segments. Did I do what they wanted me to do? Kind of interesting, isn't it? I think that's pretty fascinating. And so this segment is now divided into 5 equal segments. Therefore, I can further conclude, watch this, I could take 1, 2, and 3, and so from here to here, that's in the ratio of 3 to 2. If I were thinking of these as equal lengths, this length, let's say, is 5, 5, 5, 5, because they're all equal. And 5 plus 5 plus 5 would be 15. 5 plus 5 is 10. See how it's in the ratio of 15 to 10 or 3 to 2? Would not matter what numbers I chose. Let's try 3. I don't know. Doesn't matter. 3, 3, 3, 3, 3. 3 plus 3 plus 3 is 9. 3 plus 3 is 6. Isn't that also in the... Aha. Would not matter what length I said that those segments are. Because they're 5 equal segments, I can say they're in the 3 to 2. Or 2 to 3, whichever way I want to look at it. 4 to 1. Well, I can look at that one too. So you see how to divide something into equal segments using constructions? Why in the world would that ever be? Oh, that is used all the time. In construction, do I want this wall to be twice as long as this wall? In other words, I want it in the ratio of 2 to 1? Yeah, that happens a lot. Okay? And so they got to figure out, okay, twice, how do I do that? I'm going to find the midpoint. Do I want this length to be 3 to 2 in proportion to the other length? Yeah. Does that make sense? Now, it's not always that simple, using whole numbers, but it's a great application. Geometry, honestly, is one of the most applied math classes in the real world. We haven't even started talking about circles, and circles are one of the most that's applied. Okay? Triangles, though, I already told you about my story about the center pivots, didn't I? Center pivot. Have I told you that? Did I tell it? I'll tell you real quickly again. Okay. Basically, a farmer had to give up his farm. A friend of mine had to give up his farm. He was milking all the time, and he ended up going to like a John Deere implement place, and they gave him a job installing center pivots. Well, what's center pivot? A center pivot is, where they put fertilizer and water out in a farm. Well, this thing would just transverse to here, and that would be the farm that would need the center pivot. You know what that is called? That's called an area of a sector. You think you use geometry to find the area of the sector? Yes. Do you think you got to know the area of the sector to know how much fertilizer and water to put down? Yes. The guy was a dairy farmer, and he ended up with no geometry. You never know. It's a great story. Great story. because the center pivot can only go from here to here because there was a ditch on his land right there. So the center pivot couldn't go over unless they built a bridge, which they didn't want to do. All right. Enough of that. Any questions? Monday we'll start fresh with 12.2. We're all here on Monday, so we'll get an assignment on Monday. If you have not finished 12.1 and submitted it, which was due last night, you need to get it done.